All right, and we're back with more PyData Boston / PyData Global. And so our last non-lightning speaker of the day is Sebastian Wallko. He is a AI builder and an open source maintainer, and we're really excited to have him. So go ahead.
All right, thank you. All right, thank you. I'm Sebastian, and I will talk about the software architecture pattern that underlies most or all of the GenAI apps and GenAI frameworks that you can find today. Before I do that, a couple words about me. I am German, which you can see by the weird character in my name, and I have a PhD in social robotics or computer science from Uppsala University in Sweden. I also maintain an open source library called Image.io, which some of you may have actually used before. For example, if you've ever opened an image with scikit-image, because we are like we are the dependency that they use. Right now we sit at around 36 million downloads a month, which is pretty cool, and it was a very fun journey to go there. I moved to Boston about 5 months ago together with my wife because she's doing a postdoc at MIT. And before that, I worked as a product manager in a Scandinavian multinational news company. And the product that I was working on was the data platform, which I guess I can describe in like one sentence as like you can think of it as like a custom Google Analytics that can feed data to recommendation engines and targeted advertising models alongside doing all the standard analytics stuff. Yeah. So, but what I want to talk about now is something that a lot of you have probably noticed as well, which is that there are a lot of AI frameworks out there right now. Right? Like there's LangChain, LangGraph, AgentKit, Agent SDK, MCP Agent, what's it, Crew AI, ADK, etc., etc. Right? The list goes on. And what's interesting about that is that there is a common theme across all these libraries, and that's the one that I want to highlight today. And I want to do this in two parts. First, I want to talk about this architectural pattern, which is the core loop. And then in the second half of my talk, I want to talk a bit about context engineering, which is sort of the how do you specify the metadata that goes into your LLM to actually make it do things. Right, first up, the core loop. This is a LLM call, which I'm sure most of you have seen in one variant or another. Depending on which LLM gateway or which provider you use, the parameters will be slightly different, but these four pieces will always be there, and they will always do the same thing. You have the model that you want to call, you have the system prompt, which are the instructions for the LLM, you have the history, which is you can think of as the record of the conversation that you had with the LLM, and finally you have the list of tools, which are the functions or the things that the LLM can call or the things that it can do. And you need to specify all these four things, and then you can call your LLM. If we zoom in a bit on the history, then you can see that the history is essentially an array of objects. And there are different types of objects depending on what kind of message has been passed back and forth. And I would say there are 5 important types of messages that are relevant for us here. The first one is the user message. Then we have thinking, we have the tool call and the tool result, and the assistant message. And what they do is kind of self-explanatory. But what is important for us is that there's a very strong assumption about the order in which these objects will appear in the list. So for starters, a user message will always be followed by an assistant message, unless it happens to be the very last user message in your stack, because that happens to be the user message that we want the LLM to respond to. Also, between the user and the assistant message, you will find the tool call and the tool result. These ones will always follow each other, and there will be no other message in between, with the exception of something called parallel tool calling, which happens when one tool call contains multiple tools that the agent or the LLM wants to call, in which case you will find multiple tool result messages after the tool call. And then finally, you have thinking, which is something that the LLM does in response to input from us. So either it happens after the user message or after we send a tool call. And then you will basically find this order that you have here, which is a user message, maybe some thinking, tool call to result, a bunch of these, maybe some more thinking, and then an assistant message, and then this entire block repeats a couple of times. If the other part of the input are tool calls, which, as I said before, are functions that the LLM can call. And this is not how you actually send them over to the agent, but this is how right now we typically define them, aka right now is December 2025. not jumping ahead here. Um, so December 25, MCP seems to be the way to go to define tools, which you can see from the tool decorator at the top. And what you do need to define to send over to the LLM are three things. First, you have the name of the function, which is typically the same as the name of the tool. You have the signature of the function, which defines the signature of the tool. And usually that one is sent to the LLM in, you specify that in JSON schema. But tools like MCP will convert that for you. And then finally, you have the tool description, which is often specified through the doc string of the function. And from these three, the tool description is the most important piece because that one determines whether or not and when your LLM will decide to call the tool. So this is one of your big levers that you have when you design an agent on how you actually get it to do the right thing at the right time. It's like, is your tool description good or not? That's one of the big levers that you need to worry about. All right. Once we have that, we have the model, we have some instructions for the model, we specified the history of the conversation up until this point, we specified which tools exist. We can send all that to the model, and the model will respond with one of two things. Either it will respond with an assistant message, which we usually then show to the user, or it will reply with a tool call. If it responds with a tool call, the expectation is that we, as the application, or that the application finds the tool with the name that the LLM requested, passes the inputs to that function, calls that result, and takes that result and sends it back to the model as a tool result. And the way that works is we construct a new request, which has the exact same parameters as our first request to the model, but this time we append to the history the tool call that the LLM just did and our tool result. And then we get a new response from the model, which again will either be an assistant message or a tool call. And if it's a tool call, we repeat this entire cycle. Right? So if we write that out in a sequence diagram, the way a typical interaction with a LLM looks like is that we have the user on the one side, the app in the middle, and the LLM on the other side. And then our user sends a message, and this might be a user typing into a chatbot, it might be a user clicking a button to kick off a workflow, or like in some extreme cases, it can be a cron job that just pings our app and says, hey, let's go. And what happens then is our app takes over, builds this LLM, builds this like request that we just talked about, sends that to the LLM. The LLM responds typically with a tool call if we have that, which we then handle and send a new request. And that cycle repeats a bunch of times. And then eventually we will get an assistant message back, which we then forward to the user, at which point the user may choose to send us a new message. And then this entire cycle repeats. So what you can see is that we have sort of two loops here. One on the LLM side, which is the tool call that repeats a bunch of times. And on the other side, on the user side, we have the user message cycle, which repeats there a bunch of times. And given this flow, we get some very strong suggestions on how we should design the application layer in our LLM application, which is we start with some setup, then we wait for a user message. Once we get a user message, we launch into a loop where we call the LLM until the LLM runs out of tool calls. We get the assistant message, and then we loop all the way back around to the start and wait for the next user message. And this process is not stateless, because what happens is after the first time we go around the big loop, we keep all the user assistant message, user messages, we keep the user message, we keep the assistant message, and we keep all the tool calls, and those become part of the history for the next call that we do. And this way the user can ask follow-up questions on what just happened, because now the LLM knows what has happened before. Also, these two loops are really important, so they get specific names. The inner loop is called the trace loop, which comes from open metadata traces. Open metadata traces are collections of spans, and spans are literally just spans of time. So where this gets its name from is from open metadata, and then applied to agents, it means that we will look at the sequence of tool calls that happen over time. So a trace for an agent is just a collection of tool calls. And so if someone tells you, like, you should look at your traces, collect them, and debug them, and analyze them, what they're talking about is look at rollouts of this inner loop. The outer loop is much more easy to explain. That one is the turn loop. And that one is because that is one turn of our conversation. We start with the user, then the agent replies, and now it's the user's turn again. And that loop accumulates history. Right. If we then take this and write this into an actual Python program, I've written this in, I took some liberties so that this would fit into a single slide. But basically, we have these two loops. On the one side, we have a while true that waits for the user input, gets the response from the LLM, loops back around. And on the other side, we have the trace loop, which is also a while true that loops forever until we get an assistant message, at which point it breaks and returns the response of the agent. And this is how you would actually build it, except in practice, you would probably add something like logging or input validation or all those kind of goodies to it. Right. Why is, sorry, I should go back and explain something. This is the core loop that powers GenAI apps. And this is also where my talk gets its name from, which is the boringly simple pattern that powers GenAI apps. Because if you look online and you read stuff about agents, you'll get a lot of you get the impression that this is going to be really complicated and there must be a lot going on. But when you actually look at it, this is not very complicated. I think everybody here could do this. Now, that being said, there are complicated bits when it comes to agents, and they can be sort of a bit unintuitive. Also, LLMs in general can be that. But this part is not one of them. And assuming the last sort of 10-ish minutes that I talked made sense, then you will understand this. And if you understand this, then likely all the other bits will make a lot more sense and fall in place. Why is this the sort of fundamental pattern that powers GenAI? Well, because variations of it will give you all the different types of apps that you're likely already familiar with. If you take out the tool loop and the trace loop and you have no loops at all, you get the standard completions, which you might have seen, for example, in automated customer response, or if you want to do sentiment analysis on articles and just run an LLM call over a bunch of articles, or things along those lines. Those are all completions that you'll find there. If you have the turn loop, but not the trace loop, what you'll get is a chat assistant. Early versions of ChatGPT are examples of that. These chat with your docs features, for example, Notebook LM works like this. You have, for example, things like certain custom GPTs where you just upload a bunch of documents and then you can chat with them. Those are all examples of these kind of assistant type applications. If you have the trace loop, but not the turn loop, you'll get an agent. And examples of this one, let me think. Sorry, I'm having a bit of a blooper, but that's okay. So then you get an agent, and these are fun. Yes, this is sort of the difference between an assistant and a chat versus an agent. An agent has the turn loop and can call tools, but not it has the trace loop and can call tools, but it doesn't have the turn loop to accumulate history. Whereas an assistant has the turn loop, but it doesn't have a trace loop. And I think this is probably the cleanest way to define agents versus chats. So if someone ever asks, this is a very sort of clean way to separate between them. And I think it makes a lot of sense when you talk about them because it gives you a lot of clarity. Now, if you combine both of these, you combine the tool loop, you have the tool loop and the trace loop, you get something that I call copilots. Now, not everybody, most people don't call them copilots. Most people just call them agents as well, which I think is partly where this confusion comes from, because if this is an agent, and this is an agent, and this is a chat, then what's the difference? And it gets a bit confusing. So that's why I call these copilots rather than agents. And the reason why copilots is because they work exactly like that. They usually sit in a sidebar somewhere in your application, and you can chat with them, but at the same time, they can also modify and interact with the stuff that you're working on. And an example of this is all your coding AI tools. For example, Claude Code, Cursor, Microsoft Copilot is an example, but also tools like Claude Desktop or Complexity work like this. Right. Another cool thing about this is that if you look at completions and agents, they have a very clearly defined start and end. And what that means, because they don't accumulate history, and what that means is we can wrap them into functions. And if we can write them as functions, we can give them tool decorators. If we can give them tool decorators, we can make them tools that other LLMs can call. Which means we now have LLMs that call tools, which happen to be other agents, which then happen to be calling tools again, which is sort of fully meta. And why do I mention this? Because LLMs using tool calls to call other LLMs is sort of the gateway drug into multi-agent systems. Now, of course, multi-agent systems probably warrant an entire talk all by themselves, but I do want to give you sort of the 2-3 dominant patterns that you see when you design these systems, because once you understand the core loop, these will make a lot of sense and just sort of fall out as a corollary, if you will. which is the first one is workflows, which is literally just daisy chaining agents after another. You call the first agent, it generates an output, you take the output, put it into the second agent, generates an output, and so forth, right? Fairly straightforward. The second pattern is the supervisor pattern. And the way that works is you have your classic agent pattern, except that your agent, you have two types of agents. One is called the supervisor agent, which is a classic agent pattern, except that all its tools are actually agents as well. And then you have the actual worker agents, which have normal agent design with normal tool calls. And then what happens is that your supervisor agents calls other agents, and those agents do the work. But the supervisor agent is actually completely oblivious to the fact that it calls agents. It just does normal tool calling as it normally does. And that's how that supervisor pattern works. And if you dig a bit into different multi-agent frameworks, you will find that one of these patterns is always how things are done, or many of these actually support both. Like those are the two dominant patterns how work gets done at the moment. And then there's another pattern, which is reflection, which flies a bit underneath the sort of like the AI hype radar, but it's still really useful, so I thought I'd mention it, which is so you can think of it as like an actor-critic framework to improve the output of an agent or of your model, which is you have your agent that generates some result. You take that result, you send it to like a completion or another agent, and that completion will judge the result and provide feedback to the feedback for the first LLM. Then you loop around, send that feedback back to the agent, back to the first agent, and then the agent will improve the result. And that cycle happens a bunch of times until the last iteration, at which point that thing becomes your final result. And that seems to be really effective in getting the output quality just a little bit higher. All right, that was the first part of the talk. We basically went from like a standard LLM call all the way through to multi-agent systems. And the main message to take away is that if you understand traces and turns and the core loop, a lot of the complexity in building these things will fall right into place, and a lot of stuff will start to make sense. Right. The second part is context engineering. And the question is, what is context engineering? And I know, and if you ask people, you will get sort of different answers. Some of them will say, well, it's about how you use a RAG system or memory, or it needs to be something more complex than just pure prompt engineering. I will try to give you a more simple and straightforward definition, which is context engineering is programming for the context window. It's a very principled and structured way of figuring out what information do I need to put into my context so that my application works reliably while also not breaking the bank. It's just like this old engineering saying goes, like everybody can build a bridge, but it takes an engineer to build a bridge that almost collapses. And right? And that's what I would say is context engineering. How do you do that for LLMs? You need three pieces. You need a plan. You need a plan for what you want to do. You need the knowledge on how it should be done, and you need the tools to get the job done. And those are the three pieces that you need to define. Why? Because what LLMs ultimately care for is the immediate next step in the sequence of work that is being done. Because what the LLM does, again, if we go back to the first couple of slides, is either it calls a tool or it gives you an assistant message. Maybe in the future, some other thing will call other tools or do another assistant message, but that's going to be a new LLM call, so the LLM doesn't worry about that stuff right now. What it worries about is right now, if I anthropomorphize a bit, like right now, where am I in my task? What tool do I need to call next? And what parameters do I need to stuff into that tool? That's it. Everything else that you add to the context that doesn't contribute to any one of these three things is fluff that you add that you shouldn't be adding. So how does that look like in practice? I'm going to go for how does it look like in practice. You write a system prompt. And a system prompt is basically a very long wall of text that specifies two things. And there are better and worse ways of writing this. The way I currently do it, which seems to work very well, is I have two sections. One section on instructions and one section on knowledge. The section on instructions is literally just a bullet point list of do this, then do this, then do this, then do this, then do this. And if that gets really long, sometimes you will add subsections that have sort of specific instructions singled out. And then instead of in your main instructions, instead of saying do this, what you say is follow the steps in this subsection. That's the instruction side. The knowledge side is a bit like a miniature knowledge base. You have subsections that are on specific topics. And then below that, you have a description of what that topic is about. And as far as I'm aware, that's at the moment one of the most optimal ways to feed information to an LLM, because all the information that's relevant for this thing is stored in a contiguous block of context that is also sequential, and it has a very descriptive title for the LLM to draw attention to when needed. And those are the two pieces, and then you have tools which come. The definition of that comes through, for example, an MCP server, and that then makes up your prompt. And I know that during the talks today, a lot of people advise to not build this one big mega prompt that has everything. And I will do a bit of a contrarian take on that and say this big mega prompt actually takes you further than you might expect. And the reason for that is that current LLMs are actually getting really, really large in terms of the context window they support. So we have 1 million or 2 million tokens, which, yes, if you run really, really large prompts, it works so-so. But if you stick within 100 to 200,000 tokens, you'll barely notice any degradation due to large context. Which begs the question, how big is 100 or 200,000 tokens? And the answer is this: one Jane Austen Pride and Prejudice book worth of text. This is 200,000 tokens, right? So chances are that your application and all the context that you have is less than one book worth of text. And assuming that is the case, you can solve your problem with just dumb prompt engineering. And the nice thing about it is it's fairly easy to set up. It's actually quite cheap to run because prompts cache really well. It's also fast because it caches very well, so it runs faster. And you can go quite far with this approach. And so before you try and optimize and break down your prompt and do all that kind of stuff, my contrarian take is beware of premature optimization. Try this first and push it until the point where it breaks before you add more complex stuff. Because in practice, there's very few systems where if you add more moving parts, the entire thing gets simpler as a result. So once we have this big system prompt, we need to manage it somehow. And one way to manage it is actually through MCP servers, which a lot of you probably know from just pure tool calling. But MCP also has a feature called resources, and they actually allow you to manage prompts. The way they work, the way resources work is very similar to how REST APIs work. You specify, you take your prompt and make it and expose it as a URI on your MCP server, or you take your prompt, break it down into chunks, and make those chunks different URIs in your MCP server, and then your LLM, or sorry, your application can request those pieces at runtime when it needs them. And the way this process works is you have, once you get the request and your app starts working, it first sends a list tools request to the MCP, gets all the tools that are available or that are relevant, and then it goes and sends a get resource request for one or all the parts of the prompt, gets all of these back, builds the prompt, and then continues exactly in the same fashion as we've discussed during the first part. And that is one way of managing your prompt, which is nice because, as I said before, your system prompt is basically a very big wall of text, and it's very nice to take that wall of text and pull it out of your code base and put it somewhere else. It also makes your job a bit easier once you get to the point of putting this app out there live, because if you have it in an MCP server, then it's already exposed somewhere, likely on the web, and then building things like, A/B testing, feature flags, or the continuous deployment will become much easier because you've already built the wiring right into the system. Right, now we get to some of the fun stuff. We have our prompt, we build our application, it grows over time, the system prompt gets longer and longer. At some point, a pure system prompt will fail. And now what I want to introduce you to is what I call sort of the deadly sins of context engineering. And the reason they are context overload, context poisoning, useless data, and inconsistency. And the reason I call them the deadly sins is because you will not get any error message, you will not get any warning or notification. They will just silently break your application. And so in some sense, they're a bit like silent but deadly, kind of like ninjas, if you will. Right. So the first one is context overload, which I'm pretty sure actually some of you have suffered from this one. Has anyone ever played with an agent or built an agent that ended up being stuck in a loop of infinite tool calling the same tool over and over and over again, maybe wasting a couple 100,000 tokens or a couple $1,000 in the process? I see someone nodding in the back there, so yeah. you've suffered death by context overload. What's happening is that as your agent generates a really long trace, that trace becomes context, and context also acts as examples for expected future behavior of the agent. And if your agent happens to have in its context like many tool calls in some way, it will just repeat those. So what the LLM thinks, if you will, is like, oh, the last 20 times I was asked to perform a response, this tool call with these parameters was the right thing to do. So I suspect right now doing that same thing is probably still correct. And that's how your agent gets stuck in this like infinite loop. And that's one of the examples of how you die from context overload. The next one is context poisoning, which is like wrong information in your context window. Very few people will actively put wrong information into the context, but the way this stuff still sneaks in is, for example, in two ways. One is if your agent or your LLM modifies the world and then you don't update your context. So for example, say you have a file with some code, your agent deletes a function in that code, but you don't update that version of the file in your agent's context. Now your agent still thinks that function exists, even though it doesn't. So when it later tries to write another file, it will put that function in and try to call it, even though it doesn't exist. The other way this happens is if you have a chunking strategy, for example, for your rack that is misconfigured, and that chunking strategy splits off important information. So for example, if you have the fact like our revenue was $2 billion this quarter, that can be a true fact, for example, in like 2024. But if your user then goes and asks, what was our revenue this quarter, aka in 2025, guess what your agent will respond? It doesn't know the year, it just sees this quarter, that matches, so it says 2 billion, even though that might be complete nonsense. And that is death by context poisoning. Next one, you have useless data. And this one is a fun one, which is if you have as your system prompt grows, you will have instructions and tool calls that might not be relevant for every single task the agent can perform. This is like the example of like building a super agent. And what can happen as you have a lot of these is that your agent can run through instructions that were not meant for your current scenario, or it can call tools that you didn't intend to be called for this specific scenario. An example of this is you might ask your agent to like roll back the last commit. And the way it does that is it decides that the best, your last commit, say like it touched your database for some reason. And so your agent looks at it and goes like, the best way for me to do this is to just delete everything in production and just rebuild from scratch up until the last commit, which normally isn't how you handle production data. And that's, if that happens, and you've seen the memes online of like the agent deleting everything, that's death by useless data. Finally, there is inconsistency. And this one is a bit mean because it's a bit stochastic. Like it doesn't always produce an error consistently. And what that is if you have two or more facts in your context that are conflicting with each other. So one statement is like our revenue was 2 billion. The other one is our revenue was 3 billion. And sometimes you have this in your context and everything works just fine. And other times, your agent decides that it takes offense to the fact that you can't specify a context properly. It then divides itself by 0 and just goes completely off the rails. And you just don't know why, because even these facts don't even have to have anything to do with your actual instructions. It just decides to implode. And that is usually death by inconsistency. Right, so those are 4 reasons why your agent can fail. What do you do about that? The answer is once you start seeing those issues, you start to lazy load your system prompt. And the way that works is you divide the system prompt into smaller bits, and then you only load the bits that are relevant for the current task at hand exactly when you need them, aka classic lazy loading in computer science. And if we look at the core loop, you will find that there are 3 points in this core loop where we can do this in an elegant way. The first part is at the prompt, so when we start to initialize the agent, where we can load everything that we know we are going to need regardless of what the user is going to ask from us. That's basically the known knowns. And then after we get the user message, we can load everything into context that we now can deduce from the user message that we are going to need. That's sort of like catering for the known unknowns. Like, I don't know, I can have a coding agent that can do certain things. I know some stuff I will need to load, but for example, I will not know which file to look at until the user tells me modify this thing. Then I know which file to look at, so that's a good point for me to actually load the context of like what's in the file. And then finally, we have the ability to add context during tool calls, and that is useful for catering for like the unknown unknowns, like the stuff we didn't expect to happen. So for example, the file that the user asked us to modify actually imports a bunch of other files. Those files turned out to be relevant, and it's nice that our agent can then load those files on demand. And those are the 3 points that we have to actually add context. And a lot of the like buzzwords that you will find in the AI space at the moment are, not all of them, but quite a few of them are just sort of at the core different strategies for intelligently lazy loading context. To make an example, RAG. RAG stands for Retrieval Augmented Generation, and it's ultimately a strategy to intelligently lazy load knowledge from a database. The way you set that up is you take all this knowledge piece of your system prompt, you divide it into small knowledge blobs, and you store all those blobs into a database. You then pick an indexing strategy for your database, and then at runtime, you use that index to find and query the relevant pieces of context and load them back into the agent. And what's interesting or kind of fun about that at the moment is that depending on the indexing strategy you use, you call the thing slightly different. So if you use a vector index for your RAG, you're doing classic RAG. If you're using a graph index and a graph database, you're doing graph RAG. If you're using a B tree or a reverse index with a document database, you're doing search. Or you're doing like web search for your agent, etc. You get the idea. Or if you dare to like take this entire pipeline, and it's a function, so you can make it a tool call. If you allow your agent to use a tool call to call your RAG, you're doing agentic RAG. And that's all the buzzwords. Right, that's the first buzzword down. Second one is skills. Skills are a relatively new idea from Anthropic. They introduced this, I think they wrote the blog post like mid-October, so roughly 1.5 months ago. And what skills are is progressive loading for your instructions. So you can think of it as like the counterpart to RAG, but for the instructions on the skill and the things that the agent can do. The way this works is you take the set of instructions that you have in your system prompt, and you take the subsections you have there, and you split these subsections out into different files. And then what you do is you add a skills section to your system prompt that says these are the skills you have available to yourself with some small description of what they do. And then in your sort of general first piece of instruction, you don't say run the steps from this subsection. Instead you say load this skill and then run all the steps from this skill. And that then allows you to move some of the instructions that you don't need for a task out of the context window, and maybe it can prevent you from deleting your database because those instructions were meant for a different use case, so your agent never sees them. That's skills. Next up is sub-agents. Now, sub-agents you can think of as sort of like lazy loading for your tools, even though that's not 100% correct. The original idea of sub-agents is that you may have an agent that runs a really long trace. So it does very, very many tool calls and therefore generates a very long sequence of stuff that we add in context. And then if you have such an agent, then usually there are patterns in those tool calls, like certain things that the agent always does together. And then you can take those patterns and create a new agent, that's the sub-agent, that you then ask to run through these steps that you have as intermediary. And then what your main agent sees is not the steps in between, but just the final result step. And an example of where this is useful is, for example, if you do any kind of like search task. So rather than having your main agent run through every single tool every single file there is and load all of those into context, you just ask your sub-agent to run through all those files, find the relevant one, and then tell your main agent what the relevant file is. And then your main agent only ever loads that relevant file, and by virtue of loading only that relevant file, it saves a lot of space in the context. In practice, when you do this, you will find that a lot of the times you can take some of the tools that your main agent has and move them over to this sub-agent. And that's why I'm saying like it's sort of like lazy loading for your tools, because it allows you to push some of the tools that your agent has over into another agent. However, I should note that this only really works if the intermediate steps are not relevant for your agent, because they are now hidden from the main agent, so that's as if they don't exist. Right, that's sub-agents. The final one that I want to touch on briefly is memory. Memory works slightly different in that it's not a strategy to lazy load context, but rather it's a strategy to do personalization and lifelong learning, if you will. The way this strategy works is that you take past conversations that your user had, so past turns and past traces, and you try and extract knowledge from those conversations. So for example, if the user ever said like, I'm an expert data scientist, that can become knowledge that you then have into your system in your system prompt. Or if a tool ran through something, read a file and realized, oh, this project actually uses polars, then you might end up with that piece of information in your context. So you extract those memories from past conversations, and once you have those pieces of information, you store them in a database or you add them to your system prompt, and then you treat them just the same way as you treat other types of knowledge. And the advantage of this is that over time, as this goes on, your agent, or that's at least the ambition at the moment, your agent will learn what the context of your user is because your user has told you so much about themselves that you kind of get what they mean when they say something, because all the stuff they don't specify, you can now look up from your database. And that's ultimately the idea of memory. Like, how can we use past conversations to pull out memory, or to pull out knowledge that we can then use in the exact same way as we use knowledge from RAG or anything else? All right, that's 5 buzzwords and a architectural framework. That's quite a lot of stuff for a Tuesday afternoon talk. So I will stop here and take questions. Thank you very much. All right, are there any questions? Yes, all the way in the back. You need to scream a little bit, I feel.
Can you hear me?
Yes.
Okay. So I just was playing with this crazy idea because I was follow exactly what you said. But for the system prompt, you had the data before the conversation. But if data changes a lot, would you ever put it in the middle, like after the chat, basically, somewhere like right? Middle method? And for the reason, because
Could you speak up a tiny little bit?
yeah, for the reason that you can take advantage of caching even better.
Okay. So your statement was that I put the data in my sort of visualization. I said the data comes before the instructions.
No, yeah, I mean, your data comes like in the system prompt, right?
Okay.
But would you ever put the data in the actual user conversation after assistant messages?
Mm-hmm.
Because that way you get more, you get better use of caching.
Right. So the statement is that if you take the data or the knowledge and you make that part of the user message and you put that after the user message instead of putting it into the system prompt, you will get even better caching, which is true if your data changes.
Yeah.
If you're building like the one big system mega prompt, it doesn't matter because all your thing is specified once and then static.
Right.
So caching will still work.
If you work with something that it's constantly changing data and you have a conversation like, oh,
Yes.
would you ever do that?
So if you do have something that changes, then yes, you would actually specify that separately. Which is also the kind of the idea of lazy loading stuff only when you need to, because if anything you lazy load, you will append to the bottom of your history, and therefore it automatically just ends up afterwards. Yes, another question over there.
So I loved how you explain all the context
Okay.
concepts. What's your take on like implementation of standards like the model context protocol and how it like impacts all of the concepts you've been highlighting?
So the question is, what's my take on standardization and, for example, the model context protocol and how that affects all the other pieces of the, I guess, of the ecosystem? Right. I think it's usual. I think there's a mix to it. There's a mixed answer to it. Like on the one hand, some things make sense to standardize because then it means we can experiment more. But on the other side, GenAI develops really quickly, but it's also, you need to remember, it's a really new field. Like in the grand scheme of all the stuff we have in software, it's still fairly new and there's still a lot of experimentation. So I'm actually quite happy about the fact that there's not that crazy strong a standard everywhere, because it means people try crazy things. And if they try crazy things, something actually works. And that's very cool because it allows us to build better applications. Does that answer your question?
Okay.
Right.
Yeah, I think we're gonna have
Okay. You can find me after the talk, and then we can talk, because I think we need
so
to cut off
much.
here.
Yeah.